Right, so I'm sorry I'm not there today, but I'm going to go through the solutions to the questions from Monday, and then I'm going to start chapter 23, 24, and then my hope is that we can do the experiment. I'll be back in tomorrow and we can do the experiment tomorrow. It's not one of the ones we did in DCU, so it is one we're actually going to have to do ourselves. Okay, so the length, diameter and resistance of a piece of nichrome wire were found to be, and they give these things right, so let's see. So the length is 0.856 meters. The diameter is 0.22 divided by 1,000. So 2.2 by 10 to the minus 4 meters, and then we're going to divide that by 2. So 1.1 by 10 to the minus 4 meters is the radius. What's the last thing? Resistance. The resistance is 27.9 ohms. Calculate the resistivity. So there's the formula. Resistivity equals RA over L. No, homework. Okay, so the resistivity equals RA over L. The resistivity is, the resistance is 27.9 A. Just bring it up here. So A is the cross-sectional area. That area is a circle, so it's pi r squared. So it's going to be pi by 1.1 by 10 to the minus 4 squared. So square that and multiply it by pi. So I'm getting 3.8 by 10 to the minus 8, which I'll put in here. 0.8 by 10 to the minus 8. So that's rounded, but I have the full number held in my calculator here. And then the length is 0.856. So I have this number in my calculator. I'm going to multiply it by 27.9, and I'm going to divide it by 0.856. So 1.24 by 10 to the minus 6. Now, what are the units? Sorry, I can't remember. This is ohms. This is an area, so it's meters squared. And then this is a length, so it's meters. So that'll cancel that. So it's just ohm meters. So that is question 2. Okay. Then these 3 questions were all based on the Wheatstone Bridge. So it's R1 over R2 equals R3 over R4. And I don't know if I said this the other day, but you have to be, where is it? Here. You have to be careful that you're using the right formation, I suppose. So R1 is always here, R2 is always here, do you know what I mean? So R1, R2, R3, R4. So this is R1, this is R2, this is R3, and this is R4. And they want us to find R4. So it's 4 over 6 equals 15 over R4. If we multiply across by 6, we'll cancel that out. And then if we multiply across by R4, we'll cancel that out. So that gives us 4 times R4 equals, what's that? 90. Is 22.0. 22.5 ohms. That's question 1. Okay, question 2. All right, so same thing, except it's OR3 we don't know. So OR1 is 10 over OR2 is 20 equals OR3 over OR4. I suppose it's a bit easier here. We can just multiply across by 60. That will cancel, and this 20 into 60 goes 3 times. So 30 equals OR3. And that's that one. And then the third one. Okay. So OR1 is 10 times OR2. Ugh. Okay. Sorry, I'm going to start with the formula. So OR1 over OR2 equals OR3 over OR4 is my Wheatstone bridge formula. Did we check if that was in the formula tables book? It is. There you go. Never checked. Homework. Okay, so it says OR1 is 10 times OR2. So if I replace OR1 with 10 OR2 over OR2 equals OR... Sugar, do I know OR3? I do. OR3 is 4. So that's 4 over OR4. Now, these ones will cancel because they're both OR2. So that gives me 10 equals 4 over OR4. And then if I multiply across by OR4, and then divide by 10, I get OR4 equals 4 divided by 10. So 0.4 ohms. Right. So that was the higher level Wheatstone bridge questions. I'm going to go through the ordinary level one. Obviously, all of that is completely higher level. So, skip over it if you're not higher level. It's no harm listening to the solutions of the ordinary level ones because obviously, those questions could be asked at higher level. So in an experiment to determine the resistivity of a nichrome wire, the student measured the resistance R and length L of the wire. She repeated this for different lengths of wire. She also measured the diameter D of the wire. The student recorded the following results. So we've got a couple of lengths, resistances, sorry, I don't know if we need to draw a graph, and a diameter. Fab. Name the apparatus used in this Name the apparatus used in this experiment to measure. So the length of the wire would be a meter stick. B. The resistance of the wire would be an ohm meter. And C. The diameter of the wire, and that would be a micrometer. Or you could say a vernier calipers. Just to be clear, you can't say calipers on its own. So a micrometer or a vernier calipers. Okay. Part 2. How did the student check that the wire had the same diameter throughout its length? You not check. Measure the diameter at different points and you average. Part 3, use the table use the data in the table to draw a graph of length against resistance. So because this is ordinary level, generally speaking, the stuff you're given in the table is what you have to plot. That very rarely happens at higher level, which, if any of you are listening, is a conversation we need to have after correcting the mocks. Okay, so I'm going to throw down a graph. Length, so label, resistance. The length, grand, we just have to get up to 70, so 2, 3, 4, 5, 6, 7. Is that right? So 10, 20, 30, 40, 50, 60, 70. The other one's not so easy. We need to get to 29. 5, 10, 15, maybe twos. Sorry, so 4, 8, 12, 16, 20, 24, 28. Will that work? Yeah, it's close enough. So that is 0.04, 0.08, 0.12, 0.16, so 4, 8, 12, 16, 0.2, 20, 0.24, and then the top one here is 0.28. Okay, so 0.8 with 20 is there. 30 with 0.12. There. 40 with 17. So there's 40, there's 16. So 17 is like there. 50 with 21. So there's 21. 60 with 25. So 60 with 25 is about there. And 70 is 29. So it's just going to be a little bit off the graph, but that's okay. 70 with 29. So that's 28. So that's 29. Okay, and then we should be able, if I skinny that, we should be able to draw a nice line that looks, again, because it's ordinary level, it's like perfect data. We're very close to it. So I draw my line. State the relationship between L and R. So this is part 4. The graph is a straight line through the origin, so length is proportional to resistance. And then the last one, state the formula used to calculate resistivity. That's the one that we found here. So resistivity is this. And again, because it's ordinary level, you don't need to explain what they stand for. You can just write it down. All right, so there's the ordinary level solutions. Right, I'm back in here. So we talked about electric current. So electric current is the flow of electric charge. So if the electric current is flowing through a metallic conductor, then the charge that flows is electrons. Yeah, so we talked about all that. Then we said that electric current has 3 effects. effects. So it is the heating effect, which we're going to talk about here, the magnetic effects, and number 3 was the chemical effect. And that was at the very beginning of I think it was the very first electricity chapter, where there was the little diagram of the circuit, and the bulb showed the heating effect, the compass showed the magnetic effect, and the beaker of dilute acid and the bubbles showed the chemical effect. Yeah? Okay, so we are going to talk about the heating effect. And this is going to lead us on to electricity 1, the first electricity experiment. Obviously not the first one we've done, because we've already done like 3 or 4 of them. But yeah, it is electricity 1. It's Joule's law. Okay, so what we have here is a little circuit. So you can see at the bottom, we have the calorimeter. In here is the insulation. Sorry, this isn't the calorimeter. This is the container. I don't think they have that labelled. So we have the container, and then inside we have the insulating material. In here you can see our copper calorimeter on the inside. This thing is a heating coil. Obviously the thermometer through the centre. You've got the lid on the calorimeter for insulation purposes. To get the heating coil to work, we need a potential difference or a voltage, and that is provided by the battery. Sorry. A rheostat, we did talk about a rheostat as a variable resistor. And you normally use a variable resistor to change the current in the circuit. We have our switch over here, and then we have an ammeter, which is connected in series, which is where an ammeter needs to be connected, and I am suggesting that ammeter is reading 10 amps. Okay, so basically, oh, and sorry, down here, very clearly, a timer. Okay, so I've got 3 little experiments over here. So you can let 10 amps flow for 1 minute, and I am saying that the thermometer would record a 4 degrees Celsius rise in temperature. Because you let 10 amps flow, it's going to flow in here through the coil, and that's going to heat the water up. If you then repeat the experiment, so put cold water back in and allow the same 10 amps to flow, but this time instead of it flowing for 1 minute, you let it flow for 5 minutes, you're going to get a bigger temperature rise, bigger than 4 degrees. Yeah, that makes sense, right? So if you keep heating the coil and you keep heating up the water, it's going to give you a bigger temperature rise as recorded by the thermometer. Okay, so in that situation, the resistance is constant in that I didn't change the coil, so I used the same coil for both experiments. The current was constant. I said that the current remained at 10 amps, and what's varying is the time. So T here represents the time. Okay, and when the time varies, you get a temperature variation. So the time that a current flows affects the temperature rise. Okay, or another way of saying it is that the time affects the amount of heat energy produced. Okay, we're measuring temperature, but obviously in order to get an increase in temperature, you need more heat energy. Yeah? So another experiment that you can run with this apparatus is where you don't vary the time. So you keep the time the same, you keep the coil the same, but this time we changed the current. How would we change that? We would change it using the rheostat. So if you want the current to increase, you're going to have to turn the resistance down. Yeah? So you decrease the resistance and that will cause an increase in the current. It's going to write C. Okay, so again, if you have a 10 amp current flowing for 1 minute through the coil, you're getting your 4 degree rise in temperature. If you then bump that up to 40 amps flowing for the same 1 minute through the same coil, you're going to get a bigger temperature rise. Okay, so same thing again, the temperature rise or the heat energy produced depends on the size of the current. And here the resistance of the coil is the same. I've not changed the coil, it's the same heating coil, so whatever it's made of, I haven't changed it. The time this time is the same. So we went for just 1 minute. So what I'm varying here is the current, and when you vary the current, you get a change in temperature. So the current affects the temperature rise or the heat energy produced. And then the last one, you probably guessed it, but the last one we're going to actually change the coil. So you let your 10 amps flow for 1 minute and you get your 4 degree rise in temperature. And then what we do is we change the coil to a coil with higher resistance and you allow 10 amps to flow for 1 minute. Okay, because the coil has a higher resistance, you're going to get a bigger temperature rise. So it's exactly the same thing over here. This is a really nice example of why you can only look at 2 variables at a time. So obviously the main variable here that I want to look at is how temperature is affected. And if I want to see if time affects temperature, then I have to make resistance and current constant. If I want to see if current affects temperature, then I need to keep time and resistance constant and so on. Okay, you can only ever have 2 variables at one time. All right, so from that, we get that the heat energy, so that's this bit here. So I'm using W, I can use E, so energy or work. Yeah, so the relationships are actually that it's proportional to time. The heat energy produced is proportional to the current squared, and the heat energy produced is proportional to the resistance. Okay, they are the relationships. You are going to do an experiment to investigate these relationships, but that's what they're supposed to turn out to be. Hopefully it works. So the heat energy produced is proportional to the time. The heat energy produced is proportional to the current squared. So changing the current has a really big impact on the heat energy produced, more so than the other two. And then the current is proportional to the resistance. So if I do that thing, where you smush them together, is proportional to Ti squared or. Yeah. Now, again, this is a proportionality, so I want to introduce a constant. So we introduce a constant K, and then I can make this equals K Ti squared, or you don't need to prove it. Because this proof isn't on the course. So if K is 1, we get W is Ti squared or. Now, I'm going to divide across by T. Now, W over T. So W over T is work or energy over time. Hopefully that's familiar, but work or energy over time is power. So we get P is I squared or. And that's Joule's law. Okay, it is over here somewhere. Here. So Joule's law states that the rate at which heat is produced, so the rate at which heat is produced is W over T, which is power. Yeah, so rate refers to time, and then your heat is your energy. So the rate at which heat is produced is work over time, or energy over time, which is power, is directly proportional to the square of the current provided its resistance is constant. Okay, so there's P is proportional to I squared, and then you introduce your constant, and that gives me the formula that I developed over here. Yeah? So we'll have a look at this. Find the heat produced in a 20 ohm resistor by a current of 3 amps flowing for 40 seconds. So power is I squared or. I haven't been given power here, so I'm going to break power up into energy over time. Is I squared or. W is what we're looking for. That is the energy, and in this case, the energy we're talking about is heat. The time is 40. I is 3, and we're going to square it, and then or is 20. Multiply here by 40 to cancel that out, and multiply here by 40. So 3 squared by 20, by 20, sorry, I'm just going to ignore that for a second, by 40. So the work is 7,200, and the fact that it's an energy, a heat energy in this case, it's going to be joules. Yeah? And that's really it. So I popped a few formula in here that might be useful. So work is force by displacement, obviously back from mechanics. Power is work over time. We've just come across that there. These are newer formulas. So this one here is Joule's law I just introduced, and this one here is Ohm's law from the other day. And down here there is potentially some stuff to do with heat. So will you please do question 9 and question 13? Okay. And I'll see you tomorrow, and we will do electricity 1, which is here, Joule's law.